So, good afternoon, everyone. Welcome to the hands-on exercise for this workshop. My name is Guotao Qiu. I'm the postdoc fellow in Professor Coriolis Research Group. And before we start, I want to ask you to open this SVE.ai website. And navigate to this workshop page, and you will find all necessary Google Colab link to today's workshop. Just link to the first one, and we'll start with the DFT with the AFLOW. So all of these hands-on exercise we're going to we have today is based on this Google Colab. The benefits to use this Google Colab is that you can, if you find our exercises too boring or too simple for you guys, you can just using this code and play around with it by yourselves. And also you can like save it by yourself in your Google Drive. So after this workshop, you can still use these commands or the exercise we have. I'll start with the basic. For the people that is not very familiar with this Jupyter Notebooks, I'm going to have a very basic introduction to this Jupyter Notebooks. It's open source web applications and allows you to create and share the documents. And it contains a series of cells, and each cell will contain like the codes or the markdown cell you can write the texts in. And just by simply click this play button, and you will to execute the code cell. And I also want you guys to open this fold window. Sorry, before start, you need to sign in with your Google account first. Just open this file window to have a better experience in this exercise. So I need some of you may be familiar with these shell commands, but it will be somehow different when we are using it in the Google Colab. So it might prefix with exclamation mark or the percentage mark to execute the command like the remove or copy or create amplifiers, etc. So before we start, let's execute this cell to download the AFLOW that we already compiled before in this Colab, so everybody can use. It will only take about 30 seconds. If you occurs any errors, please raise your hand, and one of our teammates will go to help you. And you can hide this output if it's not annoying. You can have quickly verify it's working or not by running this command below, the test command. You should be able to see your AFLOW declaration without any errors. Right. So in this section, we'll mainly focus on how we're going to use this computational tools to accelerate the discovery of new materials, and especially with the use of one particular software, AFLOW. try to look at this. Try to look at the crystal structure of the aluminum as an example. It contains aluminum atoms will align in a certain pattern inside this inside and its periodic structure. And this pattern that can be focused as a find as a cubic shape, and we can like generate the whole structure by copy this cubic along with different directions. Now let's focus on this small cell that each atom is actually at the center of the each face and also the column. So the aluminum is actually it's face centered. So the aluminum is actually a face centered structure. We call it FCC. And when we talk about the structure, we mainly break it down to two parts: the lattice and the basis. The lattice will define the which refer to this geometry alignment with the different hollow sites, and the basis is the atoms or the combinations of the atoms. Once we can simply use this command to generate something, generate a geometry files, the postcard files I will talk about later in this section, to contain all necessary information that we need to describe these crystal structures. You can just simply use click this button and we'll find the structure like this one. So AFLOW binary includes over like this is not updated. It's over like 23 million something prototypes. Imagine the enormous possibilities for the new materials when we start to substituting the species to from the periodic structure to those hollow sites in the lattice. You can add different. You can create the FCC copper, FCC nickel, FCC lead, etc. into by just using this command here. And also, in fact, you can decorate this lattice using different species in the same site or the different sites. So the question is, how do we know whether this material is going to exist or not? The thermodynamically, the stable of the materials is often correlated to the low energy, and there's some equations that has already been talking this morning. And what I try to emphasize here is the expensive computational cost growth with the dimensionals about the powder of the number of the electrons, but with the DFT calculation down to the significant to the linear scaling with the electrons, number of electrons. However, it's still too expensive to solve these equations for materials which typically has more than like 10 to the power of 23 something amounts of the electrons. So the crystal structure contains a porosity in its porosities. We can use the Fourier transform to convert the crystal structure in the real space to the reciprocal space. Like Professor Oses just mentioned, like the a line in the time space and the point in the reciprocal space, the frequency space. So this all efforts we made is trying to cut down this computational cost to something we can accept with. But still, it's very hard to calculate this equation to solve to get our materials energy by hand. That's where the computer comes in with this very highly computational resources. Just what's the AFLOW mainly focus is integrate with this one DFT code is the VASP, and it's very like powerful and popular DFT software to conduct the DFT calculations. And basically, to conduct the DFT calculation use VASP, you are including these 4 necessary input files, and we're going to run through all of these files in details, and we'll ask you to do the exercise to generate it by hand for the postcard and the key points. So the INCA file will contains the input parameter. Interval is basically the parameter means of you to communicate with the VASP software. It contains all the input parameters of the directed the specified calculation you wish to perform. You can modify these parameters to define which type of calculation you want to calculate the geometry organization, the static or the band structure calculation. Also, you can control your desired procedures by the level of the convergence you need. Here you can see the example. We just show an example to do geometry relaxation here for the income. For the postcard, it indicates the position. The postcard indicates for the position. It contains the crystal structure information. Let's consider a face-centered cubic lattice of aluminum here. You will start with a header that is all the things you can write here to remind you of which system it is or for your notes. And next, you have overall scale constant, and it's something dealing with the lattice parameters, and you will define the 3 lattice parameters vectors, and also after that by the name of atomic types, the species, and how many atoms in this unit cell, and then you can choose whether you use concatenation or the direct coordinates. Also, the final you will define which the position the atoms stay in. For the K points, it dedicates how the brilliant zone is sampled by VASP. You can start with the automatically mesh generation by setting this the second line, the NK to the 0, and which you will ask less VASP to design the mesh based on your system's geometry and the size, and also choose between a gamma-centered or the M-grid, depends on the nature of the system, and specifies specific needs you need to, for your calculations. It won't make too much differences for you to choose whether gamma-centered mesh or M-grid nowadays. But generally, I will suggest you guys to choose the gamma-centered mesh to avoid all the errors. The postcard file will contain the procedure potential in your calculations, and the VASP will provide a comprehensive library of the data set for most elements. And each of these data sets including information like the number of balanced electrons, the atom mass, and the default energy cutoffs. So, just some basic knowledge about this the VASP software. The one thing here I want you to do an exercise to generate the postcard K points for the BCC structure on your own. And you can click hint here. You will find all the necessary information you need to generate these 2 files. You'll have 10 minutes, and after that we'll start to, 5 minutes. After that we'll do it together, okay? If you have any troubles or find problems, you can raise your hand, and some of our teammates will come and help you. Okay, time's up. So we'll start to do this together. At the beginning, you can try to create empty files here, and then there's a postcard, BCC structure of the iron, and try to double-click this file so you can add it on inside of this Google Colab. By starting, you can compare to what we provide of these examples here. Starting with the nodes, the system is a BCC structure of the iron, and our candidate scaling constant is something you can use 1.0 for the normal vector, and by using something like the 2.87 is the lattice parameters for the BCC structure, iron structure. And you can starting to define what's in the lattice. The BCC structure will see that it's the same, similar to the FCC structure. It will have all these three lattice vectors perpendicular to each other. So if you're using this 1.0 in our scaling constant, you need to point the length of your lattice parameters here by using something like this. But you already have this scaling constant, you can just to specify the direction of this lattice vector, something like this one. And this is for, you will see that the three lattice vectors is along to the x and y and z direction respectively. So you can just using something to simplify these lattice vectors. So after that, you have your lattice vectors. You will need to specify which species you're going to use to decorate to the structure, which is the iron. And for the BCC structure, the basics of this contains 2 atoms, and one is in the original, which is a 0.000, and then the other one is only halfway to the all the 3 lattice parameters, the center of this body. So you can just close it, and it will be automatically saved in your collab. You can also start to create the K-point file to tell VASP how to sampling K-points in the reciprocal space for your structure. Like K-points. Also, to start, you can compare to what's going on for these examples. For the nodes, it's a BCC structure for iron, and you can set the NK equal to 0 to tell VASP to automatically generate the K meshes. You can whether use the gamma center or the grid, it's not make too much differences. And for this number of subdivisions, along with each receptacle vectors, you just by experience, it will something that multiple with lattice parameter around the 20. I can say this by this way, and we do not want to shift this K-point, so it will be 0, 0, 0 here. You can find standard answers for this exercise by using the write file functions, and we'll write all the content in this cell to a file. You need to sometimes to click this refresh button if you find your some of the files or directory you create is basic in this file explorer. Also, here you can see an example of the K-points file for the band structure calculation, which Professor Oses just talked about in the morning's talking. It's very challenging to create it by hand, even we understand what's going on behind this, what's the physics behind this. So this is where the AFLOW will step in to help you to generate, to not only generate it, the improvised part, also to manage your calculations, to do the high throughput calculations, or the error handling and the post-processing. A typical AFLOW calculation will start with a single input file, which is the AFLOW.in, and it contains all the necessary information to run a VASP calculation, including the K-points, postcard, and quota. And also the AFLOW will automatically generate these individual files to streaming the setup process. To reproduce the exercise we have done before, the only thing you need to know is the prototype of this BCC structure. Once you know what the prototype of the desired structure, you can decorate it with different species by just using this one command here. You will see it will somehow different to the postcard what we generated by hand, because it's in the AFLOW will analyzes its structure and convert it to the primitive self, you can use the AFLOW to convert it back to the conventional cell, just like by using this command. You can also want to convert it back as you see to use something like AFLOW.s primer, something like this one. Yeah. Also, you can generate this complex KPath files by giving the AFLOW just the prototype and the species. You see like this one. It will somehow reduce the efforts you need to generate these files to conduct a DFT calculation. Also, you can generate the whole AFLOW files by using this command. It will automatically generate a folder under your current working directory. Under this folder, the next level, it will contain the information for the persistent potentials and the species you need. And in the next level, it's the prototype. And inside this prototype directory, you will have this AFLOW file. If you try to generate the different, like the FCC areas for the same species, but with the different prototypes, you will find also another prototype directors under the same species directories. So I'm going to try. I'm not going to go through these AFLOW files line by line, but I'm going to highlight some important things. It will contain system names and the classical binary locations, and also the MPI set if you try to run it in the high performance clusters. And also, it contains information to the different modules, like the AFLOW SYM. You can command it to ask AFLOW to conduct the symmetry analysis, to do APL and the QHA to do the phone calculations, and AGL, AEL to calculate the elastic modules or the thermal vibration factor. You can also find for each model, you can also find a very detailed explanation of this commands or this parameters meaning by just using this AFLOW equals dash readme equals to the module names. It contains all the information you need for using this module. Also, the AFLOW can specify a calculation type, like which calculation type you need, the geometry relaxation, the static or the band structure. You can also determine how many rounds of these calculations you need by simply adjust these parameters. We'll see some examples here with when you set these parameters like the relax equals to 2, you will conduct the second round of the relaxation to make sure your structure is converged, and you can just equals to the static, will only conduct the static calculations. You can also use some settings like the relax underlying static equals to 2. It will conduct 2 rounds of the relaxation and automatically followed by a static calculation. You can modify this in the in-car parameters inside this part of the AFLOW. But if there's something missing and you want to add it to the in-car file, you can write these specific parameters here. It also contains the K points setting is indicated by the K density, not the K points. But you can also have the information for the postcard and the podcast. So, actually, how did we get this? As Professor said, is how do we get these parameters for generate the in-car postcard K points or something? You can find a very detailed explanation in this AFLOW standard paper, and this paper is about how we choose these different parameters and how and do some benchmarking and some tests. And all these default settings, you can modify this AFLOW.rc file. It's normally hidden files under your root directory, and you can modify things like the MPI settings, the different VASP binaries using different versions of VASP, something to here. Not only you can generate these entire key points postcard files from the prototype, you can extract it by using this command from the AFLOW in. You will see that as long as you have this prototype, you can generate it, the AFLOW in files, and by extract things from these AFLOW in files, you can use these input files for your further calculations. There are other very useful functions of the AFLOW to play around with these input files. You can read the CI files and convert it to the postcard. You can convert the postcard to other DFT calculation code geometry format files. You can determine the number of neighbors or the oxidation numbers even if you do not try to do the DFT calculation. And to generate a supercell or the slab of this the structure you need. All this useful command you can find in the in this README of VASP. By using these commands, you can generate a detailed command list for the AFLOW. So typically there will be one VASP calculation to run at a time, but not only with this one AFLOW calculations. The AFLOW can submit multiple DFT jobs simultaneously and make it high throughput calculations. You can simply use this AFLOW run to specify which run directory path you want. Because we do not have the postcard information here, so it will have some errors. What I want to emphasize here is this log files. It will prevent the future AFLOW runs in that directory which already conduct the VASP calculations. So if you try to run the DF again in this directory, you will cut you off at this after this line and let you know this directory this calculation has already been performed. So you can either use either delete this log file or define another log file name before you try to run again for your further calculations. You can also do the post-processing by just use the one command of AFLOW, the AFLOW port those, and these are all the package and environments you need in this Google Colab. It will take about 2 to 3 minutes. So for more details about this part of the AFLOW with the DFT, you can find this in detailed explanations and the YouTube videos inside the AFLOW scope. So that's it. Any question about this part? If not, I will leave it to them.